Section 15 of the ABC of Relativity by Bertrand Russell. This LibriVox recording is in the public domain. Chapter 15. Philosophical Consequences. The philosophical consequences of relativity are neither so great nor so startling as is sometimes thought. It throws very little light on time-honored controversies, such as that between realism and idealism. Some people think that it supports Kant's view that space and time are subjective and are forms of intuition. I think such people have been misled by the way in which writers on relativity speak of the observer. It is natural to suppose that the observer is a human being, or at least a mind, but he is just as likely to be a photographic plate or a clock. That is to say, the odd results as to the difference between one point of view and another are concerned with point of view in a sense applicable to physical instruments just as much as to people with perceptions. The subjectivity concerned in the theory of relativity is a physical subjectivity, which would exist equally if there were no such things as minds or senses in the world. Moreover, it is a strictly limited subjectivity. The theory does not say that everything is relative. On the contrary, it gives a technique for distinguishing what is relative from what belongs to physical occurrence in its own right. If we are going to say that the theory supports Kant about space and time, we shall have to say that it refutes him about space-time. In my view, neither statement is correct. I see no reason why, on such issues, philosophers should not all stick to the views they previously held. There were no conclusive arguments on either side before, and there are none now. To hold either view shows a dogmatic rather than a scientific temper. Nevertheless, when the ideas involved in Einstein's work have become familiar, as they will when they are taught in schools, certain changes in our habits of thought are likely to result, and to have great importance in the long run. One thing which emerges is that physics tells us much less about the physical world than we thought it did. Almost all the great principles of traditional physics turn out to be like the great law that there are always 3 feet to a yard. Others turn out to be downright false. The conservation of mass may serve to illustrate both these misfortunes to which a law is liable. Mass used to be defined as quantity of matter, and as far as experiment showed, it was never increased or diminished. But with the greater accuracy of modern measurements, curious things were found to happen. In the first place, the mass as measured was found to increase with the velocity. This kind of mass was found to be really the same thing as energy. This kind of mass is not constant for a given body, but the total amount of it in the universe is conserved, or at least obeys a law very closely analogous to conservation. This law itself, however, is to be regarded as a truism, of the nature of the law that there are 3 feet to a yard. It results from our methods of measurement, and does not express a genuine property of matter. The other kind of mass, which we may call proper mass, is that which is found to be the mass by an observer moving with the body. This is the ordinary terrestrial case, where the body we are weighing is not flying through the air. The proper mass of a body is very nearly constant, but not quite, and the total amount of proper mass in the world is not quite constant. One would suppose that if you have 4 1-pound weights, and you put them all together into the scales, they will, together, weigh 4 pounds. This is a fond delusion. They weigh rather less, though not enough less to be discovered by even the most careful measurements. In the case of 4 hydrogen atoms, however, when they are put together to make 1 helium atom, the defect is noticeable. The helium atom weighs measurably less than 4 separate hydrogen atoms. Broadly speaking, traditional physics has collapsed into 2 portions, truisms and geography. There are, however, newer portions of physics, such as the theory of quanta, which do not come under this head, but appear to give genuine knowledge of laws reached by experiment. The world which the theory of relativity presents to our imagination is not so much a world of things in motion as a world of events. It is true that there are still electrons and protons which persist, but these, as we saw in the preceding chapter, are really to be conceived as strings of connected events, like the successive notes of a song. It is events that are the stuff of relativity physics. Between two events which are not too remote from each other, there is, in the general theory as in the special theory, a measurable relation called interval, which appears to be the physical reality of which lapse of time and distance in space are two more or less confused representations. Between two distant events there is not any one definite interval. But there is one way of moving from one event to another which makes the sum of all the little intervals along the route greater than by any other route. This route is called a geodesic, and it is the route which a body will choose if left to itself. The whole of relativity physics is a much more step-by-step matter than the physics and geometry of former days. Euclid's straight lines have to be replaced by light rays, which do not quite come up to Euclid's standard of straightness when they pass near the sun or any other very heavy body. The sum of the angles of a triangle is still thought to be two right angles in very remote regions of empty space, but not where there is matter in the neighborhood. We, who cannot leave the earth, are incapable of reaching a place where Euclid is true. Propositions which used to be proved by reasoning have now become either conventions or merely approximate truths, verified by observation. It is a curious fact, of which relativity is not the only illustration, that, as reasoning improves, its claims to the power of proving facts grows less and less. Logic used to be thought to teach us how to draw inferences. Now it teaches us rather how not to draw inferences. Animals and children are terribly prone to inference. A horse is surprised beyond measure if you take an unusual turning. When men began to reason, they tried to justify the inferences that they had drawn unthinkingly in earlier days. A great deal of bad philosophy and bad science resulted from this propensity. Great principles, such as the uniformity of nature, the law of universal causation, and so on, are attempts to bolster up our belief that what has often happened before will happen again, which is no better founded than the horse's belief that you will take the turning you usually take. It is not altogether easy to see what is to replace these pseudo-principles in the practice of science, but perhaps the theory of relativity gives us a glimpse of the kind of thing we may expect. Causation, in the old sense, no longer has a place in theoretical physics. There is, of course, something else which takes its place, but the substitute appears to have a better empirical foundation than the old principle which it has superseded. The collapse of the notion of one all-embracing time, in which all events throughout the universe can be dated, must, in the long run, affect our views as to cause and effect, evolution, and many other matters. For instance, the question whether, on the whole, there is progress in the universe may depend upon our choice of a measure of time. If we choose one out of a number of equally good clocks, we may find that the universe is progressing as fast as the most optimistic American thinks it is. If we choose another equally good clock, we may find that the universe is going from bad to worse as fast as the most melancholy Slav could imagine. Thus optimism and pessimism are neither true nor false, but depend upon the choice of clocks. The effect of this upon a certain type of emotion is devastating. The poet speaks of one far-off divine event to which the whole creation moves. But if the event is sufficiently far off, and the creation moves sufficiently quickly, some parts will judge that the event has already happened, while others will judge that it is still in the future. This spoils the poetry. The second line ought to be, to which some parts of the creation move, while others move away from it. But this won't do. I suggest that an emotion which can be destroyed by a little mathematics is neither very genuine nor very valuable. But this line of argument would lead to a criticism of the Victorian age, which lies outside my theme. What we know about the physical world, I repeat, is much more abstract than was formerly supposed. Between bodies there are occurrences, such as light waves. Of the laws of these occurrences we know something, just so much as can be expressed in mathematical formulae, but of their nature we know nothing. Of the bodies themselves, as we saw in the preceding chapter, we know so little that we cannot even be sure that they are anything. They may be merely groups of events in other places, those events which we should naturally regard as their effects. We naturally interpret the world pictorially. That is to say, we imagine that what goes on is more or less like what we see. But in fact, this likeness can only extend to certain formal logical properties expressing structure, so that all we can know is certain general characteristics of its changes. Perhaps an illustration may make the matter clear. Between a piece of orchestral music as played and the same piece of music as printed in the score, there is a certain resemblance, which may be described as a resemblance in structure. The resemblance is of such a sort that, when you know the rules, you can infer the music from the score or the score from the music. But suppose you had been stone deaf from birth, but had lived among musical people. You could understand, if you had learned to speak and to do lip reading, that the musical scores represented something quite different from themselves in intrinsic quality, though similar in structure. The value of the music would be completely unimaginable to you, but you could infer all its mathematical characteristics, since they are the same as those of the score. Now, our knowledge of nature is something like this. We can read the scores and infer just so much as our stone-deaf person could have inferred about music. But we have not the advantages which he derived from association with musical people. We cannot know whether the music represented by the scores is beautiful or hideous. Perhaps, in the last analysis, we cannot be quite sure that the scores represent anything but themselves. But this is a doubt which the physicist, in his professional capacity, cannot permit himself to entertain. Assuming the utmost that can be claimed for physics, it does not tell us what it is that changes, or what are its various states. It only tells us such things as that changes follow each other periodically, or spread with a certain speed. Even now we are probably not at the end of the process of stripping away what is merely imagination in order to reach the core of true scientific knowledge. The theory of relativity has accomplished a very great deal in this respect, and in doing so has taken us nearer and nearer to bare structure, which is the mathematician's goal. Not because it is the only thing in which he is interested as a human being, but because it is the only thing that he can express in mathematical formulae. But as far as we have travelled in the direction of abstraction, it may be that we shall have to travel further still. In the preceding chapter, I suggested what may be called a minimum definition of matter. That is to say, one in which matter has, so to speak, as little substance as is compatible with the truth of physics. In adopting a definition of this kind, we are playing for safety. Our tenuous matter will exist, even if something more beefy also exists. We tried to make our definition of matter like Isabella's gruel in Jane Austen, thin, but not too thin. We shall, however, fall into error if we assert positively that matter is nothing more than this. Leibniz thought that a piece of matter is really a colony of souls. There is nothing to show that he was wrong, though there is also nothing to show that he was right. We know no more about it either way than we do about the flora and fauna of Mars. To the non-mathematical mind, the abstract character of our physical knowledge may seem unsatisfactory. From an artistic or imaginative point of view, it is perhaps regrettable, but from a practical point of view it is of no consequence. Abstraction, difficult as it is the source of practical power. A financier, whose dealings with the world are more abstract than those of any other practical man, is also more powerful than any other practical man. He can deal in wheat or cotton without needing ever to have seen either. All he needs to know is whether they will go up or down. This is abstract mathematical knowledge, at least as compared to the knowledge of the agriculturalist. Similarly, the physicist, who knows nothing of matter except certain laws of its movements, nevertheless knows enough to enable him to manipulate it. After working through whole strings of equations, in which the symbols stand for things whose intrinsic nature can never be known to us, he arrives at last at a result which can be interpreted in terms of our own perceptions, and utilized to bring about desired effects in our own lives. What we know about matter, abstract and schematic as it is enough, in principle, to tell us the rules according to which it produces perceptions and feelings in ourselves, and it is upon these rules that the practical uses of physics depend. The final conclusion is that we know very little, and yet it is astonishing that we know so much, and still more astonishing that so little knowledge can give us so much power. The end. End of section 15. End of the ABC of Relativity by Bertrand Russell.